Hey there, science fans! Welcome to another exciting journey into the world of chemistry. Ever wonder how some reactions seem to stop, but things are still happening? That's chemical equilibrium. It's a fascinating concept where reactions appear to halt, but in reality, they're still very much active. Imagine a two-lane road with cars going both ways. Picture this: cars are constantly moving in both directions, creating a dynamic yet balanced flow. When the number of cars going each direction is the same, you have a balance. That's equilibrium. It's a state where the traffic flow is steady and no side is overwhelmed. In a chemical reaction, it's similar. The reactants and products are like those cars, constantly moving and changing. We're talking about the forward reaction, which is reactants making products. This is like cars moving in one direction on our road. And the reverse reaction, which is products turning back into reactants. This is like cars moving in the opposite direction. Equilibrium happens when these reactions occur at the same rate. It's a delicate balance where the forward and reverse reactions are perfectly matched. It's like a seesaw perfectly balanced in the middle. Neither side is heavier, and it stays level. This balance is crucial in many chemical processes. Understanding chemical equilibrium helps scientists control reactions, making everything from medicines to new materials. It's a key concept that drives innovation and discovery. So next time you see a reaction that seems to have stopped, remember, it's just reached equilibrium. The magic of chemistry is still at work. Thanks for joining us on this exploration of chemical equilibrium. Stay curious and keep experimenting. Now, here's the thing about equilibrium. It's not static, it's dynamic. This means things are still happening, even though it seems like nothing's changing. Think about our two-lane road again. Even with the same number of cars going each way, individual cars are still moving, right? That's what happens in dynamic equilibrium. The forward and reverse reactions keep happening, but at the same rate. This keeps the concentrations of reactants and products constant. Now, there are two main types of equilibrium: homogeneous and heterogeneous. Homogeneous equilibrium is like mixing sugar and water. Everything's in the same phase. Liquid. The sugar molecules dissolve and some might crystallize back, but at equilibrium, the concentration stays the same. Heterogeneous equilibrium is when we're dealing with different phases. Think about soda in a sealed bottle. The CO2 gas is in equilibrium with the CO2 dissolved in the soda. Even though they're in different phases, gas and liquid, they reach equilibrium with a constant exchange of CO2 between them. Now, what happens if we mess with this balance? Le Chatelier's principle tells us that if we change the conditions of a system at equilibrium, it will shift to counteract that change. Think about adding more reactants. It's like adding more cars to one side of our road. The system will try to use up the extra reactants, making more products to regain balance. The opposite happens if we remove reactants. The system will shift to make more reactants, using up some products in the process. Section 5. Pressure. Squeezing the equilibrium. Pressure changes mainly affect systems with gases. Increasing the pressure is like squeezing the reaction into a smaller space. The system doesn't like feeling cramped. It will shift to the side with fewer gas molecules to relieve the pressure. Decreasing the pressure does the opposite. It gives the reaction more room to breathe, so it shifts towards the side with more gas molecules. Section 6. Temperature heating things up. Temperature also plays a big role. Remember endothermic reactions? They absorb heat like baking a cake. Increasing the temperature for an endothermic reaction is like giving it more fuel. It will shift towards the products, absorbing the extra heat. For exothermic reactions, which release heat, increasing the temperature is like making it too hot in the kitchen. The reaction shifts towards the reactants, trying to cool things down. Section 7. Le Chatelier's principle, predicting the shift. This principle is a fundamental concept in chemistry that helps us understand how systems in equilibrium react to external changes. Le Chatelier's principle is like a crystal ball, giving us the ability to foresee the future behavior of a chemical system. It helps us predict how a system at equilibrium will respond to changes in concentration, pressure, or temperature. By understanding these shifts, we can control reactions more effectively in industrial processes and laboratory settings. Remember, increasing the concentration of a reactant or product will make the reaction shift to use up the added substance. This is because the system aims to counteract the change and restore equilibrium. Conversely, decreasing the concentration of a reactant or product will make the reaction shift to produce more of the removed substance. This balancing act is crucial in maintaining the stability of the system. When it comes to pressure, increasing the pressure on a gaseous system shifts the reaction towards the side with fewer gas molecules. This is because the system seeks to reduce the pressure by favoring the formation of fewer gas molecules. On the other hand, decreasing the pressure shifts the reaction towards the side with more gas molecules. This adjustment helps the system increase the pressure back to equilibrium. Temperature changes also play a significant role. Increasing the temperature favors the endothermic reaction, which absorbs heat. This is because the system tries to counteract the added heat by shifting towards the reaction that consumes it. Decreasing the temperature favors the exothermic reaction, which releases heat. By shifting towards the exothermic reaction, the system compensates for the loss of heat, maintaining equilibrium. Understanding these principles allows chemists to manipulate reactions to achieve desired outcomes. Section 8. Calculating the equilibrium constant, a practical example. Now let's get practical. In this section, we will dive into the fascinating world of chemical equilibrium and learn how to calculate the equilibrium constant, Kc, through a step-by-step practical example. We can measure equilibrium using the equilibrium constant, Kc. This constant is a crucial parameter in chemistry, as it helps us understand the balance between reactants and products in a chemical reaction at equilibrium. It tells us the ratio of products to reactants at equilibrium. Essentially, Kc provides insight into the extent of a reaction and whether the products or reactants are favored when the reaction reaches equilibrium. Let's imagine the reaction. A plus B gives C. This is a simple reaction where two reactants, A and B, combine to form a product, C. Understanding the concentrations of these substances at equilibrium is key to calculating Kc. If at equilibrium we have A equals 0.5 m, B equals 0.2 m, and C equals 0.8 m, what's Kc? Easy peasy. These concentrations represent the molarity of each substance at equilibrium. Kc equals C divided by A times B, which is 0.8 divided by 0.5 times 0.2 equals 8. This calculation shows that the equilibrium constant for this reaction is 8, indicating the ratio of the concentration of products to reactants. A high Kc means we have more products than reactants at equilibrium. This suggests that the reaction favors the formation of products, and the forward reaction is predominant. A low Kc means we have more reactants than products. In this case, the reaction favors the reactants, and the reverse reaction is more significant. Understanding Kc helps chemists predict the behavior of reactions and design experiments accordingly. By mastering the concept of the equilibrium constant, you can gain deeper insights into chemical reactions and their dynamics. This knowledge is essential for fields such as pharmaceuticals, environmental science, and industrial chemistry, where controlling reaction conditions is crucial for desired outcomes. So the next time you encounter a chemical reaction, remember the importance of Kc. It's not just a number, it's a window into the molecular world, revealing the delicate balance that governs chemical processes. Keep practicing, and soon calculating equilibrium constants will become second nature. And that's it for our practical example on calculating the equilibrium constant. Stay curious, keep experimenting, and continue exploring the wonders of chemistry. Section 9. The importance of equilibrium in chemistry. So, why do we care about equilibrium? Well, it's everywhere in chemistry. It helps us understand how reactions behave and how to control them. Think about the Haber process, which makes ammonia for fertilizer. It's a reversible reaction, meaning it reaches equilibrium. By manipulating the conditions, we can maximize the yield of ammonia. Without understanding equilibrium, we wouldn't be able to produce enough food for everyone. Section 10. Applications of chemical equilibrium. Chemical equilibrium isn't just theoretical. It's incredibly practical. It's used in countless industrial processes. Think about the production of plastics, pharmaceuticals, and even the extraction of metals from their ores. Our own bodies rely on chemical equilibrium. The balance of oxygen and carbon dioxide in our blood, the regulation of pH levels. These are all thanks to equilibrium. Understanding it allows us to develop new technologies and solve real-world problems in fields like medicine, environmental science, and material science. Section 11. Conclusion: Equilibrium, a fundamental concept. That's chemical equilibrium in a nutshell. It's a dynamic process where the forward and reverse reactions occur at the same rate. We learned about homogeneous and heterogeneous equilibrium, Le Chatelier's principle, and how to calculate the equilibrium constant. Equilibrium is a fundamental concept in chemistry, helping us understand the world around us and develop new technologies. Keep asking questions and never stop exploring the wonders of science.